the cube root of 2 plus the cube root of 4 was the catalyst for the discovery of a method for solving cubic equations.
God taught me the cube root of 2 plus the cube root of 4 in my dream. That's how I found the solution.
What kind of trial and error did he use to discover? The following is my guess. There's a famous way for solving cubic equations called Cardano's method. This method is, in a sense, hyper-technical, in that it deliberately divides the one and only unknown into two. In other words, if the unknown is x, then new unknowns u and v are introduced to solve the problem as x equals u plus v. In general, it is natural that the more unknowns there are, the harder it is to solve. However, you can solve cubic equations easily by setting two unknowns in this way. I learned about this Cardano's method during my third year of high school. When I followed up on the solution, I was immediately reminded of a certain exercise that I came across in my first year of high school. The certain exercise was as follows. Exercise: find a cubic equation whose solution is the cube root of 2 plus the cube root of 4. Of course, there are countless correct answers. For example, is one of the correct answers. Interestingly, however, the following equation is also correct. X cubed minus 6x minus 6 equals 0. As a first-year high school student, I was astonished. This was because the original equation had a completely simple form, that is, the coefficients were integers, even though the solution was the cube root of 2 plus the cube root of 4, a so-called unfamiliar number. Therefore, this fact was strongly imprinted in the back of my mind. So when I followed up on Cardano's method 2 years later, during my third year of high school, this immediately came back to me. And I felt that dividing the unknown into 2 in Cardano's method, and x equals the cube root of 2 plus the cube root of 4, might have something to do with each other. In fact, x equals the cube root of 2 plus the cube root of 4 is a divided form. The solution of cubic equations was difficult and seemed to trouble many mathematicians. Finally, in the 16th century, the Cardano's method was discovered by Scipione Del Ferro. Many mathematicians tried and failed before it was discovered. Del Ferro may have thought to himself as follows.
Impregnable. It can't be helped, so instead of solving, why don't I first examine elementary matters such as what form a cubic equation will be, whose solution is, for example, 1 plus the cube root of 2, 1 plus the cube root of 3, the cube root of 2, plus the cube root of 3, etc., which includes cubic roots.
For example, 1 plus the cube root of 2 is a solution of the following cubic equation. X cubed minus 3x squared plus 3x minus 3 equals 0. Also, 1 plus the cube root of 3 is a solution of the following cubic equation. X cubed minus 3x squared plus 3x minus 4 equals 0. These are simple cubic equations without cube root numbers and the coefficients, but in the case of the cube root of 2 plus the cube root of 3, there's no simple cubic equation that has this as its solution. At best it is something as follows, but with cube root number, the cube root of 6 included in the coefficients. X cubed minus 3, the cube root of 6, x minus 5 equals 0. Mathematicians of the time must have done a lot of this kind of trial and error. In the midst of all this, the discoverer of the Cardano's method must have happened to investigate what kind of equation has the cube root of 2 plus the cube root of 4 as a solution. Then, to his surprise, he was led to a simple cubic equation as follows. x cubed minus 6x minus 6 equals 0.
What a surprise! Both cubic roots have disappeared.
It was a surprise. Of course, this does not necessarily mean that the solution has been found, but it seems to have led to a deeper analysis of how a simple cubic equation with integer coefficients could be obtained from an unfamiliar number, the sum of cubic roots, the cube root of 2 plus the cube root of 4. As a result, this leads to the discovery of the solution, but below, I will imagine what the analysis was like. First, try cubing both sides of x equals the cube root of 2 plus the cube root of 4 equals 2 plus 3 times the cube root of 8 times x plus 4 equals 2 plus 6x plus 4 equals 6x plus 6. Examining where, in this calculation process, the cube root disappears, you will first see that the root sign disappears at the cube root of 2 cubed and the cube root of 4 cubed. The part to focus on is the cube root of 2 times the cube root of 4. Here, you see, the cube root of 2 times the cube root of 4 equals the cube root of 8 equals 2. And the root signs have successfully disappeared. That means, he must have realized that the cube root of 3 plus or minus the cube root of 9 and the cube root of 4 plus or minus the cube root of 16 would work well, because the cube roots disappear when the two are multiplied. By the way, the cubic equation corresponding to the cube root of 3 plus the cube root of 9 is x cubed minus 9x minus 12 equals 0. Also, the cubic equation corresponding to the cube root of 4 minus the cube root of 16 is x cubed plus 12x plus 12 equals 0. The point is that uv should be an integer, or rational number when x equals u plus v, so for example, the cube root of 2 plus 1 over the cube root of 2 can lead to obtain a cubic equation with integer coefficients. The corresponding cubic equation is 2 times x cubed minus 6x minus 5 equals 0. In this way, some of the unfamiliar numbers, solutions to the cubic equation with integer coefficients, can be easily discovered. The discoverer of the method must have also wanted to thoroughly find what other unfamiliar numbers existed. When he did so, he must have realized the following.
Cubing both sides of x equals u plus v yields x cubed equals u plus v cubed equals u cubed plus 3uv times u plus v in parenthesis plus v cubed equals 3uvx plus u cubed plus v cubed. Therefore, if u and v are found such that both 3uv and u cubed plus v cubed are integers or rational numbers, a cubic equation with integer coefficients should be obtained.
In other words, he must have thought that if only u and v, which satisfies as follows, is found, 3uv equals integer, or rational number, u cubed plus v cubed equals integer, or rational number. If you cube both sides of the first equation star, you get 27u cubed v cubed equals integer, or rational number. U cubed plus v cubed equals integer, or rational number. These two equations are simultaneous quadratic equations for u cubed and v cubed. Therefore, they can be solved. Then, by considering the cubic roots of the obtained solutions, u cubed, v cubed, you can find as many unfamiliar numbers as you want. Or rather, the discoverer of the method must have noticed here.
Oh wait. If I reverse my current thinking, I will be able to solve the cubic equation.
It is truly a historic moment. At this moment, he was convinced that he had solved it. All that remained was to sort out the logic. In short, for the following cubic equation, x cubed plus alpha x plus beta equals 0, if you put x equals u plus v, you get u plus v cubed plus alpha u plus v plus beta equals 0. Therefore, u cubed plus 3uv, u plus v plus v cubed plus alpha u plus v plus beta equals 0. So, you get u cubed plus v cubed plus beta plus 3uv plus alpha u plus v equals 0. Thus, if you find u and v satisfying, u cubed plus v cubed plus beta equals 0. 3uv plus alpha equals 0. X equals u plus v is the solution to x cubed plus alpha x plus beta equals 0. From the second equation star star, 27u cubed times v cubed equals negative alpha cubed can be obtained. Therefore, together with the first equation star, the following simultaneous quadratic equations regarding u cubed and v cubed can be obtained. Solving this quadratic equation and taking the cube root of u cubed obtained gives u. By substituting this u into the equation star star, v is obtained, and u plus v, or x, is obtained. Since there are 3 cube roots of u cubed, including multiple solutions, 3 solutions for x can be obtained by the above process. However, in terms of logic, rejoicing here is just lacking the finishing touch, or rather, it is incomplete. Because the above logic only says, if u and v are this and that, then it is a solution. In other words, you do not know if you have obtained all the solutions of the cubic equation x cubed plus alpha x plus beta equals 0. For example, when looking for the solution to the quadratic equation x squared minus 64 equals 0, it is like saying, if you substitute x equals 8, the left side becomes 0. Solved. Solved. Another solution, x equals negative 8, is missing. But at least one solution has been found. Therefore, if the solution is named as lambda x cubed plus alpha x plus beta equals 0 is factored as x minus lambda times second order polynomial of x equals 0. From this, you get following equation. Second order polynomial of x equals 0. This is a quadratic equation, so 2 solutions can be obtained from this. Therefore, you can see that x cubed plus alpha x plus beta equals 0 has a total of 3 solutions. In other words, you can see that the 3 solutions obtained earlier are all the solutions of the cubic equation. I believe that the above is how the discoverer of the method arrived at the solution to x cubed plus alpha x plus beta equals 0. By the way, the left side of this cubic equation does not include the x squared term. The general cubic equation, x cubed plus ax squared plus bx plus c equals 0, can also be solved by placing x plus a over 3 equals y, because this leads to reduce to the form y cubed plus alpha y plus beta equals 0. Above, I boldly imagined the thought process of discoverer of the method to the cubic equation based on my high school experience related to the cube root of 2 plus the cube root of 4. I may have been too daring, but I'm pretty sure it's not far off. How is that?
Your imagination is mostly correct. Thanks for remembering me.
Thanks for watching so far.